Hello students, good morning. Today we are going to talk about helium neon laser. It's popularly known as a He-Ni laser. A He-Ni laser is a most widely used laser. It has a continuous wave output. It is easy in construction and reliable in operation and can laser on almost entire visible and IR region. You can see the figure here. It's a finished version of a helium neon laser showing you the tube, the power supply and the optical resonator cavity. In helium neon laser, the transactions occur in neutral neon atoms and helium plays the role of selectively populating the pertinent energy levels of the bicollisional excitation to achieve population inversion. Translation levels are very specific and this laser can laser on almost every wavelength of the visible region. Here you can see some prominent lasing wavelengths where yellow is 594 nanometers, green is 543.5 nanometers, orange is 612 nanometers, and red is 632.8 nanometers. There are certain other wavelengths also on which this laser can laser. They are infrared region, you have 1.523. Lambda 1 is defined as 3.39 micrometers, lambda 2 as 0.633 micrometers, and lambda 3 is equal to 1.15 micrometers. In a helium neon laser, the transitions are very specific in nature. Here you can see some of the principal transitions where you see that the 2s2, that atomic level transitions from 2s2 to 2p4 give you a 1.15 micrometer laser, and a transition from 3s2 to 2p4 gives you a 0.6328 micrometer laser, and a transition from 3s2 to 3p4 gives you a 3.39 micrometer laser. These are the prominent wavelengths on which a helium neon laser lasers. Here you can see the construction diagram of a helium neon laser. What you see here in the figure is a glass tube and a gas mixture is in the tube. The glass tube is connected to the optical resonator cavities through the flexible rubber bellows. These flexible rubber bellows act as shockers and they help in supporting the glass tube. There is the optical resonator cavity you can see in yellow color. The yellow colored strips from the optical resonator cavity and the tube rests on the rubber bellows shown in the figure. The power supply is also there. You can see the power supply. Now you can view the energy level diagram of a helium neon laser. What you see here is F1, F2 and F3 denotes the helium energy levels, and you can see here very clearly that the third energy level of helium is almost closely proportional parallel to the sixth energy level of neon. So the collisional excitation, that is, first you put energy in the neon in the helium atoms, and this energy is being bombarded to the neon atoms, and then the excitation takes place to the neon atoms and the lasers are formed. What you see in the energy level diagram is a 3.39 micrometer laser, a 632.8 micrometer laser, and a 1.15 micrometer laser. You can also see the laser transitions. This 1410, if you see, represents the energy levels of E5, 1410 energy levels of E3, and 25 the energy levels of E2, and so on. In the 3s level, the transition from E6 to E5 gives you a 3.39 micrometer laser, whereas in the 3s level only, a transition from E6 to E3 gives a 632.8 nanometer laser. If there is a transition from E4 to E3, then there is a 1.15 laser. Though this diagram which is given to you has shown you all three lasers lasing at the same time, but it does not happen. Normally it is designed for one wavelength so at a time. So either you can have an E6 to E5 transition, or you can have an E6 to E3 transition, or you can have an E4 to E3 transition for a 1.15 micrometer laser. You can also see here that due to the spontaneous emission, the atoms get accumulated from E3 after laser transition. The atoms get accumulated from E3 to E2 level of energy. And what can happen is, again, the energy given to the system from E1 can populate unnecessarily the E2 level also. So in order to stop this unavoidable population inversion, what is done is there is a reduction in the diameter of the tube so that the spontaneously emitted photons, atoms, are striking by the walls of the tube, losing energy, and then coming down to the ground level. This is the mechanism of population. You can see here that a discharge tube, which is made up of glass, contains a mixture of helium and neon gases in a ratio of 10:1 to 5:1, where the optimized value is 7:1. The gas pressure inside the tube is maintained to 1 torr. The process of excitation of the laser is as follows. A helium interacts with a photon, and then it is excited helium, and then the excited helium will interact with neon, and the energy is transferred to neon. So the neon is excited. You can see the construction and working. Small differences in the energy are taken up by the kinetic energy of atoms after collision. Upper laser levels 3s and 2s have a lifetime of nearly 10 to the power minus 8 seconds, which is suitable for lasing. The glass discharge tube is typically of the order of 30 centimeters length and 1.5 centimeter diameters. But in order to get an optimized output, the diameter of the tube are output dependent. Hence, the length may vary from 10 centimeters to 50 centimeters, and the diameter may vary from 1.5 to 5 centimeters. As the tube length and the diameter are to be optimized for a particular output, the pressure inside the tube may change or may vary. Hence, the best gain can be obtained, or you can say the optimized gain can be obtained when the product of the pressure and the tube diameter lies in the range of 2.9 to 3.66 torr millimeter. This has been optimized. That is, when the product of pressure and tube diameter, pressure of gas inside the tube, and the tube diameter lies in the range of 2.9 to 3.66 torr millimeter, then you get the best output. The output of a helium laser shows strong dependence with the power supplies. Hence, they are to be meshed. It is important to design a power supply for a helium neon laser. A helium neon laser can be designed with external mirror and internal mirror type cavities both. The internal mirror type cavity is suitable for small output lasers, whereas these external mirror type cavity lasers are suitable for large output lasers. The excitation may also take place at lower energy levels, which can lead to an unrequired population, as I discussed it earlier, which may lead to unrequired population inversion. The effect can be reduced by reducing the diameter of the tube so that the excited atoms may collide by the walls of the tube and get de-excited to the ground level. This is termed as collisional de-excitation. So you can say a helium neon laser works on both the principles. The collisional excitation, the excitation is done by collision to neon ions from helium ions, and the de-excitation reduces the probability of unwanted population inversion. There are special design considerations for a helium neon laser. As we know that a helium neon laser can laser on so many wavelengths, so it is possible to have lasing at more than one wavelength at a time. In order to prevent such a thing, the resonator cavity mirrors are coated with multi-layer citric coating, which are highly reflective at one wavelength, that is the wavelength which is to be amplified, and absorptive at other wavelengths which are not to be amplified or which are to be avoided. Now we talk about certain advantages of helium neon laser. A helium neon laser has a high coherence length. This is typically to the most gas lasers. In case of helium neon laser, the coherence length varies from 20 centimeters for multiple longitudinal modes to more than 200 meters. It all depends on the cavity parameters and mirrors and ethelons used in the design of the optical resonator cavity and the laser. The stable central wavelength, the typical emission wavelength of the helium neon laser is about 632.816 nanometers in air. But due to the presence of ρV that we can discuss later, that is the radiation energy density, there is an interaction of radiation and matter, and there is a broadening of the laser beam. So it may broaden from 632.816 nanometers as well. Very stable oscillation frequency can be obtained. The central wavelength of the non-stabilized laser can drift in the range of 1 picometer, which is still fairly good comparing to the other laser types. It has high spectral purity. Spectral purity means it moves around one wavelength, that is 632.816 nanometers, very strictly. Only a slight difference or deviation is there from the wavelength. That is why we call it a spectral purity. Helium neon laser medium features several emission peaks. However, it is relatively easy to force the laser to oscillate in just one of the emission bands. As I told you, the presence of ρ makes it happen. That is the line shape function we have to talk about. Once it is done, no spontaneous emission or emission from other bands is detectable. The good beam quality and alignment is obtained. Longer is the glass tube, easier it is to get good Gaussian beam profile. As you know, a laser beam can be identified for its spectral purity from the Gaussian beam profile only. The Gaussian beam, more peak has a Gaussian beam, more shorter is a Gaussian beam, more purified is a spectral purification in a laser beam, and more broad is a Gaussian beam, then there are more frequency components present in the beam. So good beam quality and very good angular and spatial alignment with respect to the laser housing can be achieved. It is low cost and it is widespread in such applications as, first, it was used in barcode scanners and CD players, driving a cost down, and now a laser of 2 to 3 milliwatt output power costs typically less than €1,000. It is cheap. Now, what are the drawbacks of a helium neon laser? There are certain drawbacks also of a helium neon laser. It has a short lifetime. Helium atoms are very important for reducing the lasing threshold of the complete laser. But these atoms are small and tend to diffuse through the walls of the glass tube. The diffusion of helium atoms is the main reason of the short lifetime of the helium neon laser, which is often in the range of 1,000 to 10,000 hours, and that is less than 1 year of 24/7 operation. This is considered the main drawback of a helium neon laser in any industrial application. Long warm-up time is again the another drawback of a helium neon laser. Manufacturers specify typically warm-up time of 10 minutes, which is not tolerable for industrial applications requiring continuous operation. However, in the situation where the laser has to be frequently turned on and off, this is a big drawback, which typically means that one has to install mechanical shutters which open up for laser exposure, whereas the laser is electrically on for almost all the time. That is, the laser must run continuously, which further decreases the lifetime of the laser. The low output power of the laser is again a disadvantage. Most powerful helium neon lasers emit from 35 to 50 milliwatt of output power, not more than this. This is low comparing to a 100 milliwatt or a 200 milliwatt TEM00 mode output from same semiconductor laser. Even frequency stabilized is 360 stabilizes at 633 nanometer lasers, emits 70 milliwatt to 100 milliwatt of narrow line width power. Very bulky in nature, a 35 milliwatt output power helium neon laser is about 1 meter long. It is not cost effective anymore to buy it now. This is an important parameter now, nor to store or transport it. Such big but not very powerful lasers are typically used in scientific labs or in some sophisticated holographic applications only. High voltage helium neon lasers often use above 1500 volts. Such high voltage also creates certain risks for the people and equipment around. Now we can talk about certain applications of helium neon lasers. Applications: helium neon lasers, particularly their standard devices emitting at 632.8 nanometer, are often used for alignment and in interferometers. They compete with laser diodes, which are more compact and efficient but have less convenient beam profiles. They are less spectrally efficient also. Some helium neon lasers are serving in optical frequency standards, that is, you can talk about the spectral purity here. The laser is extensively used in science laboratories for doing parametric determination of laser beams. Thank you.